I know the last time we've had conversations around how do we think about handling data? Today we'll be taking that a little bit forward by thinking about some of the measures of central tendency. But before we go into that, there's a problem we need to solve. Say right now we have an NGO, an agency that wants to fund a project in Kenya, and now they have to make a decision about what exactly do they want to fund. They know they want to fund something that has to do with improving the health of preterm babies, and they want to fund, and this decision is going to be based on which condition has the highest incidence in Kenya. Now, they're considering whether to fund prevention of intraventricular hemorrhage or whether to fund hypothermia, meaning that kids, preterm kids cannot maintain their temperature. So sometimes that temperature falls too much. That can be a cause of death also. So they're just wondering, what do we need to fund? And they're turning to us and saying, how do we know which of these conditions has the highest incidence in Kenya? The easy option, one. So do we have people who has ideas for these, our consultancy? What do you think we should do? How do you think we can answer their question? They need to know whether to fund neonatal sepsis or whether to fund intraventricular hemorrhage in neonates. Which one has the highest incidence? They want us to answer that question in this class. How would you go about solving that problem for them? Now I can't see people's faces, so I can't tell if somebody wants to respond. Somebody can just unmute and tell us what ideas. How do you think we should go about this?
Okay, so I'll probably want to do like a cross-sectional study to establish the prevalence of that outcome in the group, right? And maybe see which of those groups actually have a higher incidence of both, and the predetermining factors, the exposure that can lead to that outcome in both groups, right? And then see whether funding would support the intervention we hope to give for the most at-risk group for any of those cases you have mentioned. Yeah.
So what's the name? So when we contribute in this class, you can quickly just mention your name, and then so I know how to address you. That's a very interesting contribution. Yes. We might be interested in assessing what's the prevalence of each of the conditions that affects preterm babies in Kenya. Because our funders want to fund the condition with the highest incidence, we need to figure out what the incidence is. Now, my next question is, say we have narrowed down to just two conditions, either sepsis or hemorrhage. We know that either of these two would have the highest incidence. How do we compute? How do we go about obtaining this incidence for sepsis? Sepsis among preterm babies in Kenya, or for hemorrhage among preterm babies in Kenya? How do we measure that? How do we get that information in the next couple of weeks? What do you actually want to measure? Where do you want to go? Who do you want to collect data from? Is there someone else who wants to say something about that?
Good evening, I'm Yusuf. So for the neonatal sepsis, I think we have to first look at the population at risk, which is neonates, basically children within the first week of their life. Then those are the population at risk. Then I want to look at the number of them that are actually coming down, it's neonatal sepsis, basically. So for the other category two, we want to look at the population at risk, as well as the number of them that actually come down with that particular outcome.
Okay. Well, so I mean that's interesting. So essentially, there are two measures that you've told us that we need to get. Number one, we need to get all the neonates that are in Kenya. We need to get that number. And then we need to get the number of how many of them are coming down with sepsis and how many of those are coming down with hemorrhage. Okay, so our funders are expecting, want to make a decision within the next 2 weeks. Do you think we'll be able to get the number of all the neonates that are in Kenya between now and the next 2 weeks?
It's possible.
Okay. It is actually
It's
possible.
possible if there is a repository. So if we want to look at medical records, if, for instance, in the case of if Kenya is like Nigeria that has a national health management information system that all facilities report to, we can look at retrospective data, maybe for the most recent data in the past 2 months, and see the occurrence of both groups from that repository. Yeah.
So that's one solution for us to look at repositories and see what information already exists. I mean, there are several problems with repositories, but that's not what we want to discuss today. But say our funders want primary data. They want us to go out there now, today, see how much, get an estimate of neonatal sepsis, get an estimate of neonatal hemorrhage. Now, the issue is that it's going to take a whole lot for all of us who are in this class right now. If we all go into Kenya now, trying to find that information from hospitals, we cannot get the information even about the number of neonates we have in Kenya between now and the next 2 weeks. The main point of that exercise is that the most precise measures for us are population parameters. If we want to think about neonatal sepsis in Kenya, the most, let me say, correct thing to do would be to go to Kenya, count every single neonate in Kenya, and find every single one amongst them that has sepsis. And then those who have sepsis, that number will be the numerator, and every single neonate, the number of all the neonates will be the denominator. But far too often, such an exercise is too onerous, costly, and time-consuming. And that is why some very smart mathematicians have come up with ways to help us to limit that problem. If we cannot, so what can we do so that we don't have to go all the way throughout Kenya looking for every single baby before we can get a sense of whether babies are getting more of neonatal sepsis or are getting more of neonatal hemorrhage? The answer to that was something you discussed in the last class, and that is sampling. Some very smart mathematicians have come up with theories that have been validated that has shown that, we don't necessarily have to talk to every single one. We don't necessarily need to find every single baby. If we sample babies appropriately, if we apply the appropriate thought process and techniques into sampling those babies, we can as well estimate the number of babies, the proportion of babies that are having neonatal sepsis in Kenya, or that are having neonatal hemorrhage in Kenya without having gone to every single baby. Is that clear? Now, the next question I have is that, say we decide to sample 1,000 babies. Let's leave the intricacies of sampling. That's what you've talked about before. So we've appropriately sampled 1,000 babies, because we can do that within a month. We can do that within 2 weeks. And we found the proportion of them that has neonatal sepsis. We found the proportion of them that has neonatal hemorrhage. The number we find, for instance, maybe out of that 1,000 neonates we found 100 of them having neonatal sepsis. That would be 10%. If we had counted every single baby in Kenya and every single baby that had sepsis, what do you think would have been the number, the estimate we would have gotten for neonatal sepsis? Now I want contributions. Now we've done our sample. In our sample, we found 10%. If we had had the resources to count the whole population and find and estimate, and basically calculate, that's not an estimate anymore, calculate the total, the total amount, the proportion of babies who have sepsis in that total population, would it have been the same as what we got from our sample? Now we have to respond to this one. You're either a yes or a no. Is there anybody who wants to?
I think no. It depends on quite a number of factors that goes into us, carrying out our own research for the sample size that we use. We have to know what is the power of our study, what is the effect size of our study, because I think these are very important in doing some extrapolation for the general population.
Well, that's true. It's so. Is there anybody who has a different idea?
I would say that if the sample is representative, then yes, we should expect to get the same proportion affected in the population.
That's also a very reasonable thought. Is there someone else who has something else to say? No, why do you say that, though? Why do you say that?
If your sampling process is carried out appropriately, then you would be measuring persons that are representative of the entire population. And so the data you glean from that, you should be able to extrapolate that to the population.
Okay. Is there someone else who has another contribution? Anybody else who has a different idea from the two things we've heard? We've heard someone argue for why we should not expect to find the same. We've heard somebody argue that, well, if the population is representative, we should be able to, the estimate we get from the sample should be the same thing as we would have gotten from the population. Have we counted every single baby we have in Kenya? You see, for both, the reasoning is correct in both situations. I mean, from both points of view. We should expect to get the same number, but we should also expect not to get the same number. And here's what I mean. You see, whenever we take a sample, when we say a sample is representative, we need to understand what that means. What that simply means is that every single member of the population that we're trying to think about, for instance, every single neonate in Kenya has an equal chance, or at least a known chance, of ending up in the sample that we collect. And because we know because we understand the chances for each person to be in that sample, we can think about whether whatever we find from this sample would represent what we find in the population. If we do, in fact, give everybody the same chance of ending up in that population, in that sample should represent the total population. But when we say represent the total population, what does it mean? It does not mean that that sample is going to exactly be the same as the total population. No. It means two things. It means that the more this sample approaches the main population, the better our estimates are. Now, let me explain what that means in basic language. Say in Kenya, we have 100,000 neonates. And now we're sampling 1,000 of them. If you sample them well, for instance, say we pick a neonate, if we sample them well, it would give us an estimate. That estimate should not be far from what we would have gotten if we had counted every single one of them. It is not going to be exactly the same thing. Because, come to think about it, Every time you take a sample, remember, if I randomly sample 1,000 kids out of this 100,000 kids, if somebody else wants to do the same story and samples 1,000 kids, remember that you're not going to pick every single kid in my sample. No, they're going to pick another 1,000 kids. They will have some from my sample, some that are not part of my sample. If a third person comes, in fact, if every one of us in this class uses a random generator to identify kids, 1,000 kids out of that 100,000 kids, hardly would we find two people that would have exactly the same set of kids. Therefore, the estimate that each of us will get every time would not be exactly the same thing as what we would have gotten if we are taking the whole population. But we expect those estimates, if our samples are representative of the population, those estimates should approximate. Therefore, they should be close to each other. And one thing that our sampling theories found out is that if all of us in this class did each of our own samples and made our own estimates, if we look at the average of the mean of our estimates, the average of our estimates would tend to approximate the population parameter. Does that make sense? So one thing we can do is to say, for us to be able to answer this question for our clients, rather than every one of us just go and try to count every single baby in Kenya, which can be very difficult because they will let us into certain hospitals because we will need, all sort of IRB for different hospitals and all sort of issues. Why don't each of us just run a random generator, select 1,000 babies, everybody go ask your questions from those 1,000 babies and estimate the incidence of neonatal sepsis in each of those babies. When we get all of those estimates, some people might get 9.2, some might get 9, some might get 8.4, some might get 10.3. But when we take all those numbers together, it gives us a good sense of what is the range of values. What is the range of values between which it is likely that had we actually counted the population, we would have found the exact, had we actually counted the population, what exact proportion would we have found? So generally speaking, because these mathematicians were able to do those esoteric calculations that really established this idea that if we take repeated samples from a population and we find the average of those repeated samples, the mean of the means from those samples approximates the mean from the population. The other thing we should know about it is that the larger those samples, the closer, the more precise those means would be, and the more likely that the average of those means would actually coincide, would actually converge on the population, on the incidence as we counted the whole population. But has anybody seen anywhere where people have said, okay, let's sample and resample about 100 times so that we can find the means of all the means? No, nobody actually does that. What we do is that we take one single sample. That's what we do. We take one single sample. But those mathematicians who validated the theory that if you took multiple samples and you find the average of those samples, that the average kind of converges on the average of the population itself, they've also shown us that, when you do this sample, how does it differ? What is the likelihood? To what extent does each sample mean? What extent does it deviate from the population parameter? But more precisely, not the population parameter, but from the means of means that we have just said would approximate the population parameter. To what extent does it deviate from that? Because if we know that, for instance, if we sample just 1,000 babies, we'll get an estimate. And we have a sense of how far away from the actual estimate can this estimate be. That might just be enough for us. I'll give you an example. Say we sampled 1,000 babies now, for instance. And when we calculated neonatal sepsis in these 1,000 babies, we found that the incidence of neonatal sepsis is like 21%. Then we calculated the incidence of hemorrhage. We found that the incidence of hemorrhage is 5%. Is that enough for us to answer? I mean, now, have we answered the questions that our funder needs or not? Now I need answers. I need opinions on that. Okay, we've sampled 1,000 people, 1,000 neonates from Kenya. We found that in these 1,000 neonates, 20% of them had sepsis, and only 5% had hemorrhage. Have we found an answer for our funders?
I don't think so, because we are not sure how much representative is what we'll find out. So we have to give more information around our study, basically.
Okay, is there somebody else who has another idea? Another opinion? Have we answered the questions based on this? Can our funders go ahead and decide that now we know what to fund because we know the condition that has the highest incidence? Can I get one more person to at least weigh in on that? Well, go ahead.
I don't think so, because there are still other parameters that we would like to know. For example, we want to know if the mean is actually a representative of how far is it from the population mean. And also we need to infer from the usual means or the previous mean that was done, is it significant?
Okay. So, what this comes down to is that, remember that the question we want to answer is sepsis more common than hemorrhage? Now, one thing we know, though, is that because we didn't count everybody, right? If we took 1,000 samples multiple different times, even though we've taken that sample just once, we know that if somebody else conducts this study and counts how many kids are having sepsis, they would come up with a different estimate, right? If we tell our funders that, oh yeah, sepsis.
Sir, we cannot measure for example, some sepsis or hemorrhage for the whole entire population. We have a limited population. We can apply for this sepsis or hemorrhage.
Yeah, so we're saying, and that's what I'm saying, that because we have a sample population right now, we know that if people take different samples, they will come up with different numbers. But what our funder would want to know is that, well, now that we know that 20% is what you have, what actually is the range of values? What is the bound? What is the range of values that we think that, well, it is very likely that the population value falls in this range? And that's what I talked about earlier in the central limit theorem. It is the idea that, if we sample this population repeatedly, and we measure the average of, for each of the average of these estimates from all these samples, the average of these estimates should approximate the actual number in the population. So, for instance, if we took this 1,000 sample several times, and some of them come to 20.1, some come to 19.8, some point. If we take the average of all those numbers, the average would almost be the same thing as had we counted everybody in the population. The question now is that because we never had the resources to count the whole population, we have some important information. We know the mean from our sample. We do not know the mean from several different, from multiple samples. But there's something that we can calculate that gives us an idea of how far away from each other the results of these samples could have been. And that, in fact, is the standard error. Because if we take a sample and we calculate it, we make an estimate from our sample, if we do know the standard error also, the standard error gives us a sense of how far away the multiple estimates would have been had we conducted multiple samples. The multiple estimates would have been from what? From the actual value. So, I've spent this whole exercise because sometimes the idea of how we move from samples to populations and the justification for why our sample, the estimate from our sample, is not going to be identical, but should be representative, should be comparable with what we get from the population, from the population parameter, is very important. And there comes the role of the standard error. Because at the end of the day, the standard error gives a bound on how far away we are likely to be away from that parameter. So once you calculate your estimate from your sample, and you calculate your standard error also, that way you can say, well, now we know that our estimate for sepsis is 20. Having factored our standard error into it, we know that now our confidence interval or the range of values is, say, from 19 to 22, from 19 to 21. That is very good information for our funder, because if the range of values is 19 to 21 or from 15 to 25, it tells us that, well, even though we don't know what exactly is the population parameter, we know that the population parameter cannot be as low as the estimate for neonatal hemorrhage. And that's enough information for them to be able to take the decision they need to take. In essence, the point I'm making is that a lot of times when we are trying to answer questions, it is not the precise number from the population that we need to be able to answer or take a decision or to answer the question we need. What we need is an answer, an estimate that is good enough to tell us the relative order of things. And if we have a sample and the standard error, we can compute the confidence bounds around our estimates to be able to know the relative order of our estimates. So now I'm going to go into how do we actually compute the standard error from the estimate that we have gotten. So in the previous class that you have learned, that you attended, you must have learned about the standard deviation. The standard error is essentially the standard deviation divided by the root of n, where n is the size of the sample. Remember that the standard error is not the same thing as the standard deviation. Rather, the standard error is a figure that the way you can understand this is to think about that thought experiment of sampling and resampling your population multiple times and computing estimates from each of the sample you get. Now, when you calculate the standard deviation in all those samples, that is exactly what the standard error approximates for you. But because we would not do this sampling and resampling all the time, mathematicians again have bailed us out. They've they've developed for us a formula that helps us to get the number we would have gotten had we done that experiment, or at least something that approximates that number. And that is the standard error. And how do we calculate the standard error? Is that in our sample, when we calculate the standard deviation in our sample, we divide it by the square root of the size of our sample. So that is what the standard error is. So if you look at the data set that we have here, looking at the ages of 10 resident doctors, remember that the mean is what? The addition of all the ages divided by the size, the sample size, which is 10 here. So when you do that, the standard deviation is what? But to get the standard deviation, you estimate, you calculate the amount of deviation of each of the ages from the mean, meaning that you subtract each of the ages from the mean. That is the individual deviation from the mean. Now, when you have the individual deviation from the mean, so when you have the individual deviation from the mean, and then you calculate the standard deviation from the mean, now you have to divide it by the square root of the sample size, which is 10 in this case. And that is how we compute standard errors. Hopefully, when you get to the lab, you can practice a lot more the computation of the standard error. So I spent a lot of time earlier on to motivate the importance of being able to compute, being able to estimate, calculate our standard error from our sample, because that standard error eventually would be useful for us in being able to say that how close and within what range would our population parameter actually be had we had the opportunity to count every single member of the target population. Now, is there anybody who has any question on the concepts we have learned so far? Or is there anything that's not yet clear about the standard error and why it is important, and how it helps us in being able to understand how our how our sample mean relates to our population mean? So now that we understand that, now we will go to what we call measures of central tendency. Well, these are measures. Now, so for instance, one problem that arises all the time. The way we think a lot of times is about averages. If we tell you, when you go to a new city, the question you ask is not, for instance, if you want to move to a new city, the question you ask is that, what is the average temperature in this city? When you want to choose a profession, for somebody who wants to choose a profession based on how lucrative or not it is, the question you ask is, what is the average salary that people get in this profession? Or if you want to estimate whether tuberculosis is an important disease in an area, what you would ask is, what is the average number of people that develop tuberculosis in a year? The issue, though, is that when people talk about the average, we kind of have an idea of what we all mean. But depending on how we go about it, people might end up with different conclusions. So I will be talking about, the first thing we will talk about is the mean, or what people would call the arithmetic mean, or what many people would call the average. Essentially, what the mean, how we compute the mean, is basically summing together all the values, and then dividing the sum by the number of values. Say, for instance, we have 20 people, and we want to estimate how rich or poor are these people. What we do is to sum together their wealth, and then what, divided by 10, the total number of people that they are. If we have 10 kids in a class and we want to ask how old or young are the kids in this class, the average age in this class, what a lot of people are thinking about, what they want to know is the mean, which is add together all the ages of the kids in the class and then do what? And then divide it by the number of kids in the class. But here's the problem. Let me give you an example of a class, for instance. Say we have a class, okay, not a class. Say we have a football team. But this football team has like 5 players that are under 10 years old. But then for some weird reason, we have some other 6 players that are over 20 years old. You know, when we calculate the mean of this, when somebody asks you, maybe the first thing I should ask you is that, okay, we have about 6 players who are over the age of 20, and we have about 5 players who are less than 10. If somebody comes and say, "Oh, what is the average? What is the average age of your teammates?" What would be a good number? I'm not asking for exact calculations here. What would be a good number? What do you think what do you think would be an informative answer to give this kind of person?
The mean of median.
The what?
15, 16.
Mean of median.
Okay, 15. Well, but here's the problem. In this team, is there anybody who's 15 years old?
No, nobody.
Well, there's nobody who's 15 years old. So when we say that, when people ask you for the average, people can mean so many different things. Because when you tell them, "Oh, the average age of our teammates is 15 years old," and then somebody can think, "Oh, well, maybe this is the team for a lot of teenagers." And then say they want to buy some kind of gift, they start thinking about what kind of gift would be good for teenagers. Except that when they bring the gift, there will be nobody in the team that the gift will be suitable for. Why? Because there are 5 people who are less than 10 years. And then there are 6 more people who are more than 20 years. So when people ask you about an average, you need very precise. The precise question is, are you asking for the mean or the median? Because even though these are you asking for the mode? Because even though these are all measures that describe a data set, what exactly they tell us about the data set can be kind of different. The only condition where they tell us the same thing about the data set is when the data set is normally distributed. And we will come to that concept of normal distribution in the future. So basically, you see, you see how basically we have calculated what the mean would be. But given this person who wants to buy a gift for members of the club, that information telling them the average is 15 years can actually mislead them, can lead them into buying some kind of gift that would not be suitable for any member of the group. Now, for this person who wants to buy, if this person told you that, what I'm thinking about is to buy gifts for members of the group, but I want to buy a type of gift that, well, it might not be suitable for everybody, but at least it's suitable for most people in the group. So what is the average age of the people in the group? Will your answer be different for this group? What would be your answer if this person had explained like that?
Use the median.
Yeah, I think I will give are over 20 because they are the majority. So I think the
Okay.
mode here was some.
Somebody has said the median. I would ask you to tell me more why you want to give the median. Somebody has said they want to give over 20, but you give two examples. One is because they are the majority. But we know that the person who's asking us a question is not asking for maturity, he's asking for, well, I want to buy a gift that will be suitable for most people.
I think that's the most people, majority of them.
Yes.
I think
So in that case, if you question here, I want to buy a gift for most people that would be suitable for most people. So what's the average age of people here? The answer to that would be the mode. Because the mode, the mode here would be, say, let's say that, 22, 6 people are 22, 5 people are like 9. That is what the mode would be. Now, there are places where the median is also, the median is the appropriate measure for us. For instance, no, let's not take a lot of time on that, because apparently when we understand this concept, we have a good idea of what these concepts are. The median essentially is the middle figure. So now, okay, we have 5 people who are less than 10. We have 6 people who are more than 20. Well, I'm just trying to buy a gift for, the middle person. So what we do is we list all the over 20. We list all the under 10. And because there are 11 people in a team, we look, when we arrange them in ascending or descending order, we pick number 6. We pick the middle person. Basically, where does number 6 come from? The number of people in the sample is 11. We add 1 to it, making 12, and then we divide it by 2. So when you order the observations, whether in ascending order or in descending order, now you take the total number in the sample, add 1 to it, and divide it by 2, and that gives you the position of the median. And then you pick the median number. So now we're going to go to different kinds of tests. But before we go on to that, do people have any questions on mean or measures of central tendency?
Sorry, I just wanted to ask a question. The n+1 divided by 2, does it matter whether or not the sample size is even or odd? Was of the opinion that if it is odd, you are likely to find a middle value. But if it is even, 2 values may be at the center, and in that case, you add them and divide by 2. So I'm a little confused with the n+1.
No, that's correct. It should not be confusing. So if you have an odd number, if you have a odd number of items, yes, the middle value is very, it's very obvious, right? If you had an even number of samples, well, at the end of the day, what the median ends up being is the arithmetic mean of the 2 middle figures. So say you have 12 observations, right? If you have 13 observations, the median is very clear. It's going to be the 7th observation. But
I wonder if.
Go ahead.
Sorry, I was going to say, I wonder if we want to take a quick break, and then when we come back, we can speak some more about comparing means and medians. What do you think?
Okay, we can do that.
Okay. So maybe how many minutes do you think?
So we can take a brief break for about 10 minutes.
Okay. Thank you. Yeah. So we can come back in 10 minutes, everyone.